In this video, I am going to be defining the kinetic energy formula from a basic understanding of your formulas for motion. So consider the following object travelling from point A to point B with initial velocity u and a final velocity v. Now, the point travelling from A to B has some mass, which I've just wrote there, m, and it has an initial velocity of u. It's going to travel some displacement or distance to a point B, where it's now travelling at a final velocity v, where t represents the time in which it took to get from point A to point B. So that's what I've written here. S represents the distance covered by the object, and t represents the time taken for the object to travel from point A to point B. Therefore, the average velocity of the object can be expressed in two forms. Now, this is like the two forms for average velocity that we defined in the formulas for motion in a previous video. So we've actually got two formulas for motion here. And if I rearrange this formula here, I get this one down here, which I've called equation 1, and it's referring to the change in displacement. Okay, so it's referring to how far the object travelled. If I substitute equation 2 into equation 1, so if I put this into here, where I see v up, I'm going to put v plus u divided by 2. It's going to give me an equation which I'm going to call equation 3. But we can also define an expression for acceleration. Now, that expression is rationally obtained by subtracting the initial velocity from the final velocity and then dividing it by the time. So what we have here is change in velocity over a period of time, which is defined as the acceleration. If I rearrange this formula to solve for t, I get this, which I've called equation 4. T equals v take u divided by a. If I go over the page and continue on, what I'm going to then do is look at substituting this across, I'm going to look at substituting equation 4 into equation 3. And if I do that, this is what I get left with. I haven't called this equation 5 because what I can do is I can simplify this stuff on the right hand side. And if I go about doing that, I get to a simplified expression for equation 5, which I've now called equation 5. And I've said which rearranged gives v squared equals u squared plus 2as. So if I rearrange this in terms of v squared, I can get my v squared equals u squared plus 2as formula for motion. So this here we looked at in a previous video as to how we get this. Now, consider the work done by the object. Okay, now the object, just to refresh our memory, is right here. Object with mass m travelling at initial velocity u. The work performed by that object is equal to the force multiplied by the displacement. Okay, this is our formula for work. And I've called that equation 6. But I've also then went and defined next to it what force is actually equal to in terms of mass and acceleration. Okay, so this force is this force, and I've defined it as mass times acceleration and called it equation 7. You then probably see what I'm going to do with MA, and that is substitute it into equation 6 to give me what I'm going to call equation 8. So what I've done is I've taken MA and I've moved it and put it where F is to get this equation here. The work equals the mass times the acceleration multiplied by the displacement. And I've, as you can see, labelled it equation 8. Note, the work, W, is simply the object's change in energy from point A to point B, where change in energy can be called delta E, such that delta E equals W. So all I'm saying there is that the work when we talk about work, in this situation here, all work is the change in energy from this point to this point. So how much energy was used to get from point A to point B is what we define as work. And what I've done is simply to get to this point from equation 8 to equation 9, I've just simply recognised that work is a change in energy. So work is the same as an energy change. So work is going to be, or the units for work will be joules, just like energy is. Now I'm at equation 9. What I'm going to do is substitute equation 5 into 9 to give me a new equation, which I'm going to call equation 10. Now, equation 5 is back up here. Okay, so I'm going to scroll this back up. Equation 5 is up here. Now, it's giving us a change in displacement. So we're going to substitute for change in displacement. So where we see change in displacement down here in equation 9, change in displacement, we're going to substitute this v squared take u squared divided by 2a. And that is what we get left with here. Now I've cancelled out my a's, and then I expanded the brackets to get half mv squared minus a half mu squared, which I then factorised. Now, assuming that the object, and let's suggest that the object had an initial velocity of 0, so it was stationary, okay, before it got to, at point A it was stationary before increasing its acceleration to a final velocity. And if we let the u value equal 0, and we substitute 0 for u into this equation here, we will be left with the energy for the final velocity equal to a half mv squared, which is our equation for kinetic energy. So what we've done is we have arrived to our kinetic energy formula. The kinetic energy at a particular velocity is equal to a half multiplied by its mass multiplied by the velocity squared.